I made slides to help me illustrate some concepts, so you guys
Oh,
can follow along. I'll just type the URL here. Alrighty. Okay, let's get started. Okay, so for task 1, there aren't any tests other than making sure your old tests don't fail, right?
Mhm.
So some groups that do task 1 first, then go on with task 2 and 3, and then they encounter some bug that they think is related to task 2 or maybe task 3, but it actually came from task 1. Right. So what I recommend is do task 2, 3, and then do task 1.
Okay.
All right. The goal of the buffer cache is to pretty much replace every block read with cache read and every block write with cache write. Right. So after you do task 2 and 3, if you follow this interface, it becomes really easy to plug it in.
All right.
All right. Okay, so let's just dive into task 1 then. Right off the bat, you have this struct called cache entry, and I assume you're keeping track of 64 of these, right? That's good. Each of these cache entries will keep track of some sector, and then it stores the data from the sector, right here.
Yeah.
Okay, so I guess it wasn't exactly clear like what size of data is, but I'm assuming you just want to store the entire sector, right?
Yeah.
Okay.
I think so.
Mm-hmm. So we know that the size of sector is like 512, right? And the size of an int here is 4, whereas the size of a character is 1. So I believe it should be car 512.
That makes sense.
You could actually do an or int, and then this would be 128. But I just think characters are easier with.
Yeah, because they're 1 byte. So
Yeah. Okay. And you want to do clock algorithm, right?
Yeah.
Okay. You have a global lock. Okay, yeah. So the only thing that you're missing. Wait, actually, okay, here, you're initializing valid to be 1, right? But I think valid should be initialized to 0. And then when you actually fill in the cache entry with data, you would then set valid to be 1. Maybe that's just like a me thing, but for notation, that's usually what valid means.
entry duty. Yeah. Okay. Yeah.
Okay, so the only thing that you're missing is the synchronization for task 1. And again, there are no tests for task 1 other than making sure your previous tests don't fail, which means that task 1 is going to be graded by some reader who pulls your latest commit and looks at your buffer cache implementation. So make sure that you write it with like nice code and stuff. But some context. So last semester, our head TA Sam realized that the buffer cache solution I've been endorsing for many semesters has so many flaws with it that he made the synchronization requirements much, much more stringent. Like it was so strict that no single group got it completely correct. So he ended up writing an entire design doc for task 1 on his own, and he gave it to all students. Right, and this thing is like pages long. So I could send this to you if you want, but this is the 100% buffer cache. What we are accepting this semester, we've relaxed the synchronization requirements. So we're now accepting this buffer cache solution that is like, 50% correct, but it still works.
Nice.
Okay. So these slides depict the 50% correct buffer cache. And I think going from your current solution to this 50% correct solution is very easy because all you need to do is add a lock per cache entry in here.
Okay.
And you already have the big lock for the entire buffer cache. Okay, so how this works is as follows. We have the big lock for the entire cache. When we iterate through the entire cache, we must acquire the big lock first. And then we have a small lock per cache entry. So whenever we are reading, writing, or changing an individual cache block, we must first acquire the small lock. So let's say we want to read from sector 21. We first acquire the big cache lock. We then iterate through the cache and we find the cache entry with sector 1 data, sector 21 data. After we find it, we release the big lock and acquire the small lock. Right, so in terms of concurrency, during this time, another thread can access the big lock and acquire the small lock for other cache entries. Right, so that's how we get concurrency. Does that make sense?
Yes.
Okay, yeah.
Okay. Yep, and then as soon as we are done reading from sector 21, we would then release it. Right, and then,
Why is it necessary to have both the big one and the small ones again?
yep. So let's say I only have the big lock, right? If I acquire this big lock and then I read or I find the cache entry with sector 21 and I'm reading for it, while I hold this big lock, other threads cannot concurrently read from other cache entries because they need to acquire the big lock.
Right.
But I currently hold it and I'm currently reading from just one sector.
What if you just had the small locks? Then
Mhm. So what if I just had the small locks? So let's say I'm iterating or my cache is completely filled and the sector that I want is not in the cache. Let's say I want to read sector 40, right? I would then choose some cache block here. I would acquire the lock and then I would start replacing sector 21 with sector 40 data, right?
yeah.
Okay. What happens during this time? What happens if there's another thread that comes in and says, I also want to read sector 40, but then we aren't done loading in sector 40's data in here, right? So what ends up happening is that we load sector 40 data into two cache blocks,
Raise cache lock and acquire.
right?
Cache.
So you can think of this big cache lock in terms of protecting the cache's metadata, like which blocks it holds. And then these small locks protect the individual cache block and it serializes access within that cache block only. All right. In other words, whenever you're evicting a block, you must acquire the big cache lock.
Okay,
Okay, so does this make sense?
I think so.
Okay. And of course, there's like, it's only 50% correct. There's a whole bunch of edge cases and things that are wrong with this design, but this is what we are accepting this semester. Okay. And that's pretty much task one. Any questions?
No.
Okay. So let's talk about task two then. Okay. So nice job. You're keeping track of your direct pointer, indirect pointer, and doubly indirect pointer in inode disk. You only wanted one direct pointer?
Yeah.
Okay. Yeah, it turns out that one doubly indirect pointer is sufficient for 8 megabytes of data anyways.
Mhm.
So any combination of pointers that involves at least one doubly indirect pointer is correct.
Oh.
Yeah. Okay. Very nice. In my opinion, writing byte to sector to match with all your pointers is probably the hardest part of this project because there's like no good way to debug it. So what I recommend doing is creating a chart like this. Right, like this is a chart that I filled out for this scheme of pointers. Like if I want to access the first 512 bytes starting at offset 0, I use direct pointer 0. And then if I want to access the 512 bytes starting at this offset, I would use the second direct pointer and the indirect pointer, and so on and so forth. You can access these slides in the future and follow these equations to help you fill out this giant table.
Mhm.
But that's that. The fields num files and parent are not needed in inode disk. This parent fields, I'm assuming you wanted it so you can keep track of the directory of this file, right?
Yeah.
Okay, so when we talk about task 3, we'll talk about why we don't need this. The only thing that you need are your pointers, and this boolean is directory.
Okay.
All right. Okay. So that's like part 1 of task 2, writing byte to sector. That's part 1 of task 2. Part 2 of task 2 is extending your files, right? And as you guys nailed it, you're going to be using this function called free map allocate, right?
Mhm.
Cool. So you mentioned you will modify the function free map allocate to get non-consecutive regions to files. Well, that's good. Yeah, perfect. So extending files, you have a really good plan. Basically, whenever you want to extend a file, you compute how many free blocks you want, and then you try to allocate it with this rewritten function. And then if there's not enough, you just fail it. You also realize that if we are going to remove the global file system block, you must have a block on the free map. That's good. The 2 locks that you're missing, though, are, let's go here. There's a global list of open inodes in inode.c. You need a lock for this.
Okay.
And instruct inode, whenever you're changing open count and deny write count, and maybe even removed, you need a lock for this as well.
I see.
Yep. So 3 locks in task 2. Remap, inode, and open inodes. I think you guys also forgot to mention, part of this task is you remove this field from struct inode.
Oh yeah.
Right. And then does it make sense as to why we do that?
Because we're using the inode disk itself to store the pointers.
Okay, yeah, that's correct. A fully fleshed out answer would be the spec says you can only have 64 cache data blocks in memory, right?
Mm-hmm.
If your open inodes list contains 128 inodes, each of the 128 inodes would also then contain an inode disk, and then you would violate that constraint, which is why we must remove it.
Oh, okay.
So in the future, if you want to go from inode to inode disk, you will have to block read from this sector. Block reading from this sector gives you this inode disk. So there's already a bit of redundancy here.
I see.